So chapter 5 is a very interesting and important chapter because it deals with the energy involved in chemical reactions. And just as a quick review, you should know coming into the class, but there is such a thing as the law of conservation of energy. Now, that's not exactly the current understanding of it. We say that energy cannot be created or destroyed, only changed from one form to another. We now know that you can convert from mass to energy and energy to mass. So the correct law would be, that the law of conservation of mass energy. Okay, but we're going to simplify it for this class and just look at the energy changes. And we are going to assume that any changes between mass and energy are small enough that we are not going to take them into account. Okay, and that is basically simplifying this enough that we'll be able to do simple calculations. So with the law of conservation of energy, we need to understand the number of types of energy. So what are the different types of energy that we have? This is where people shout out things. Kinetic energy. That's where things are moving, right? What else? Potential energy. So what's potential energy? Potential energy is stored energy, but that doesn't narrow it down very much. What are those things up there? Light. And how do they work? Oh, what made it do that? Electrical. Wow, it must be Monday. We're not very alive here. What other types of energy are there? Thermal. And I heard somebody say chemical energy. Is that this kind of energy or another kind? Is it, yeah. So the energy stored in chemical bonds is something that is important. It is a type of potential energy. Okay, and there's other types that we can worry about. One, hopefully, that you are hearing this. Right, sound energy. Okay, now I don't really need you to just be able to list all types of energies, but I want you to be aware of the different types of energy that we can have changes with. And we're going to focus on a couple of specific ones for this chapter. One is the potential energy. Okay, now potential energy, I want you to understand, has a number of different ways that we can do it. Okay, there is the potential energy due to gravity. Like I have this marker, right? If I let go of it, it's going to go downward, right? Because it has some gravitational potential energy to it. Oop. Okay, I also have this where if I stretch it out, okay, so it had an elastic potential energy, right? Those are mechanical types of stored energy, but we also have other kinds of stored energy. And one of those is the type of energy that we find in chemical bonds. And we want to spend a fair amount of time learning how to describe those changes in energy. So this section, we're going to focus on something called thermochemistry. Thermochemistry is a subset of something called thermodynamics. Okay. Now, have you ever heard the word dynamic before? What's dynamic mean? Changing, right? Okay, so we're going to take a look at the energy changes in chemical bonds. Okay, in order to do that, in addition to the law of conservation of energy, we need to define a few things. Okay, and we're going to start with something really simple. Okay, we're going to refer to something as a system. Okay, and a system is a very simple term. Okay, a system is whatever we define it as. Okay, and whatever we do not define as the system is everything else. That's the surroundings. If I take the system plus the surroundings, I get the universe. Okay? So it's not just the stuff that's immediately surrounding our system, it's everything else. Everything else. Okay? And we need to talk about a sign convention. And I'm going to apologize because physics doesn't necessarily use the same sign convention. And we're going to say that anytime energy goes into the system has a positive energy change. And anytime energy goes out of the system, it's negative. Okay? Now, in addition to energy, stored energy that can cause motion, we also need to understand a couple terms. First is heat. You guys know what heat is? Okay. Heat is very simply energy goes from something hotter to something colder. Okay. Now we know temperature-wise, temperature is a measure of the average kinetic energy of the particles. So something hotter, let's take a simple system where the two substances are the same. Something hotter is going to have faster moving particles, and something colder is going to have slower moving particles. When they come in contact with each other, the faster moving particles will collide with the slower moving particles, speeding them up, slowing down the faster ones, speeding up the slower ones. That transfer of energy is heat. Now, it always is that the higher temperature has a greater kinetic energy. It could be that they're larger molecules and are moving slower, but you get the idea, right? But there's another type of energy that we need to take into account going into and out of our system. And I know heat's a four-letter word, so is the other one I'm going to put up here. And that's work. Now, we're not going to spend a lot of time on work in this class. However, it is important that we understand it. And again, we are under the same sign convention here. If I have an increase in energy in the system, we're going to say it's positive. Okay? So in other words, if work is done on the system, it's positive. If work is done by the system, it's negative. Okay? And if I take a combination of heat and work, I get something called the internal energy. And that's given the symbol U. Okay, so we probably need to pay attention to heat and work and the fact that we're going to use some symbols for these, right? Okay, what would be a good symbol for work? W. Good. What about a good symbol for heat? H would be a good symbol for heat, but we're not going to use H because we're not the ones who are creating this convention. There's a lot of things we could use for heat, and lots of them would be good. But we're going to use Q for heat, okay? Is that a good one? Yes. Why is it a good one? Because everyone else uses Q for heat, not because it was a really good idea to begin with. Okay. This is the convention that we're going to use. Q represents heat. Okay. And again, heat is energy that goes from something hotter to something colder. Okay. So that's that transfer of energy. Okay. Couple more things. Okay, so while we have the system and surroundings here, now if I want to measure the work, okay, I'm going to tell you this: work is not a state function. Okay, now you're thinking state function, isn't that like levying taxes? Wait a minute, so the state doesn't work on it. That's not what I'm referring to. Okay, a state function means something depends only on the initial and final state. Now, work can be defined as force times distance. So if I go here and I move over to here, a certain amount of work was done. And if I move back here, a certain amount of work was done. Okay? Now, the change in my location is 0, right? But the work is not 0. So work is not a state function. Heat is also not a state function. So it's going to be good for us to be able to measure something that we can only have to worry about the initial and final conditions. We don't have to measure it completely through the entire system, okay, through the entire process. So we're going to use this. Now, U is internal energy of the system. And without going through how we get to this, but basically, through a combination of heat and work, we're going to get something called enthalpy. Okay. Now imagine we are burning. Say that's a burner there, and it's burning, and I am releasing heat. Okay. What else is happening besides the release of heat? Well, that heat release is actually causing the gas molecules to expand and move, right? So a certain amount of work is done. So I can't just measure the heat given off by a chemical change. I have to take into account that work. And if I do this at a constant pressure, I get something called enthalpy. Okay? H is enthalpy. And you can think of it as the energy stored in the chemical bonds. Okay? And we can measure the initial and final enthalpy states. And a change will be dependent only on the initial and final state. So even though work and heat are not state functions, enthalpy is a state function. It's not the only one, but it's the one we're going to focus on in this class. Okay. Now, in order to be able to work with this, we need to understand a few things. Okay. First of all, which direction does heat flow? Hotter to colder, right? Okay. Second thing, how do we measure heat? That's not as easy, right? So if we want to measure temperature, we just pull out our handy dandy thermometer and we determine the temperature. But heat's not as easy, okay? Because heat's an energy, and measuring that energy change is a little bit more difficult, okay? In order to get to the point where we can measure energy, we need to understand that not all objects absorb heat the same. Now, if you don't understand this, I'm going to use an example, okay? So imagine a toilet seat made of metal, okay? It will conduct heat away from you very fast, okay? Maybe that's why we don't see metal toilet seats very often, right? Because it's going to feel really cold, even though it would be the same temperature as a toilet seat made out of another material. Because it doesn't take much energy for that. So it moves heat away and it warms up fairly quickly, okay? It doesn't take as much energy to change the temperature of metal as it does something like for example, a plastic or water, okay? So if we take the amount of energy it takes to heat an object, we get something called heat capacity. Now, heat capacity is the amount of energy it takes to raise the amount of heat it takes to raise the temperature of an object 1 degree Celsius. That's heat capacity, okay? And heat capacity is specific to the object. That object could be a marker, it could be a cup, it could be lots of things, whatever we define it as, okay? Now, the heat capacity can be useful for us in some cases, but what's going to be even more useful for us is to understand that different substances absorb heat at different rates. And if we look at the amount of heat it takes to raise the temperature of a substance, we're going to be looking at something more, a little bit more definitive. And that's going to be specific heat capacity. So for heat capacity, we would have to measure every single object that we work with, okay? We'd have to determine the heat capacity of every single object because it would depend on the size of the object and the material it's made of. Now, heat capacity is given the symbol of a capital C. Specific heat capacity is given a lowercase c, okay? Now, there are some books that refer to specific heat as S period, H period. I don't like that, okay? We're going to use C for specific heat. And we actually have the ability to measure temperature changes. And if I have an object and I know the temperature change, and I know its heat capacity, I can measure heat, okay? Now, likewise, if I know the amount of matter that I have, and the type of matter, I can calculate the specific heat of that object or substance by taking mass times the specific heat. Now, a couple things that might be good to know. The specific heat capacity of water is 1 calorie per gram. Or in SI units, okay. Now, where have we heard calories before? Okay, calories are a measure of energy, right? Now, I will tell you, when you look at food calories, okay, the calories that you see in food are actually kilocalories. And you know, for people on diets and everything, you know, the calories in a candy bar are really kilocalories, right? Okay. But yes, if you read the nutrition information, those calories that we see in food are actually 1,000 calories. And the calorie is the amount of energy to increase 1 gram of water 1 degree Celsius. And 1 calorie is 4.184 joules. Oh, wow. That's the same number, isn't it? That makes sense, right? So if I can determine the amount of energy it takes to increase the temperature or decrease the temperature of an amount of water, I can measure a heat change, right? Now, in addition, if I remain within the system and no heat goes out of the system and no heat goes into the system, the sum of all heat changes must be 0, right? So let's say I have a container of water and I put a hot object in there. What's going to happen to that water? Its temperature is going to go up. So if that is a completely closed system, the energy that goes from the hot object to the water will have a sum of 0. How's that work? Well, there is a heat change, right? The water has a positive heat change because heat came into it, and the object would have a negative heat change. We can say that very simply. That within a system, the sum of the heat changes is equal to 0. Or if I only have 2 substances involved, Q hot plus Q cold equals 0.